Okay, so we're going to look at certain ideals that we've seen before, and we're going to try to determine if they're prime or not. So firstly, if we look at the ideal generated by 9, which is an ideal in Z, we want to know, is it prime? So which of the following are prime? Now, you might be thinking, well, you just said that in the previous one that prime elements generate prime ideals. And while that's true, that's an if-then statement, and this element 9 we know is not prime. It doesn't necessarily mean that the ideal that it generates might not be, is not prime. We only know that if it is prime, then the ideal it generates is prime, but we don't know the opposite direction. So we're going to have to just apply the definition with some intuition that probably this is not a prime ideal. So let's notice that 3 times 3 is 9 is in the ideal generated by 9. And let's also notice that 3 nor 3 are a multiple of 9. So neither of those guys is in the ideal generated by 9. So we have a product being in our ideal, but neither of the elements in the product are in the ideal. Thus, this guy is not prime because we found an example of a product which was in our ideal, but neither of the terms of the product were in our ideal. So the intuition was right here to think that this is not prime. Nevertheless, we do have to argue it, and this is how one would argue it. To the contrary, let's look at the ideal generated by 11 in Z. Well, we know that 11 is a prime element of Z. It has no factors. And prime elements generate prime ideals. By the theorem that we proved. So the ideal generated by 11 is prime. And let me observe something here. So this is not part of this, but let's observe something for a second. Z mod 11 is a field. It's F11, and that is a field. Just going to observe that. Oh, let's also observe this up here as well. Z mod 9 is Z9. This is not a domain. Why? Well, it's very much related to it not being prime. We have these elements 3 and 3 that are going to be non-zero here because neither 3 nor 3 are in the ideal generated by 9. Yet their product, when we multiply them together in the quotient, then land in the ideal, so become 0. So I just want to observe these two things here that will formalize in a little bit. All right, let's do another example. Let's look at the ideal generated by x squared plus 1 in R adjoint x. Okay. We will show in a little bit that in a PID, so we will show that x squared plus 1, we show that in a PID, irreducible implies prime. We know that in a domain, prime always implies irreducible, but it's not true that you can go backwards necessarily. But in a PID, you can. So in particular, x squared plus 1 is irreducible. You cannot factor it over R. You would have to factor into linear terms. And the only factoring of this into linear terms will involve complex numbers. Our coefficient ring here is R. And so by the fact that we will prove this guy that we're gonna, that would be helpful here, but I just want to tell you, we'll get to it in a little bit. This tells us then that x squared plus 1 is a prime element. Thus, the ideal it generates is also prime. Its prime elements generate prime ideals. Okay, let's notice here that what happens when we take R adjoint x and we mod out by x squared plus 1, we saw already this is the same as C, which is a field. Very interesting. All right, let's do another one. D. Let's look at x squared minus 1, the ideal generated by x squared minus 1 in R adjoint x. Well, x squared minus 1 factors, right? X squared minus 1 is x minus 1 times x plus 1. The very presence of this factoring seems to indicate that this should not be a prime ideal. In particular, we know that the product x minus 1 times x plus 1 is in the ideal generated by x squared minus 1. But neither x minus 1 nor x plus 1 are in the ideal generated by x squared plus 1. Or x squared minus 1, sorry. Because when you're in this ideal, you're multiples of something of degree 2. So your degree is at least 2. Whereas x minus 1 and x plus 1 have degree 1. So they are not in that ideal. So we have a product being in our ideal, but neither of the terms of the product are in our ideal. So this ideal, the ideal generated by x squared minus 1, is not prime. And this mirrors what we know from the integers, right? So when you factor, you're composite, and you're not prime. And so we see this happening on the level of ideals now. All right, so that's the last example that I want to do. Actually, hang on, that's a slight lie. So let me do one more example. I'm going to do the last example. We're going to look at the ideal generated by x squared minus 5x plus 6, x to the 4th plus 2x cubed minus 10x squared plus 5x minus 2 in R adjoint x. I want to do this just to highlight something. So this guy is polynomials over a field. R is a field. So we have a PID. And we have two elements generating an ideal in a PID. But it's a PID. So this ideal is principal. It's principally generated by something. So in particular, it's not clear if either of these elements you can factor, but it doesn't matter because we're not looking at them individually. We want to know sort of what the principal generator, information about the principal generator. That will tell us whether or not this is in fact a prime ideal. So if you run the Euclidean algorithm, you will find the GCD is x minus 2. So how do you run the Euclidean algorithm? Well, you either do it yourself with long division, repeated long division, or you ask Sage real quick to see that the GCD is x minus 2. Which means that this ideal, let's call the ideal I, so I don't have to keep writing it over and over again. So I is equal to the ideal generated by x minus 2. Since x minus 2 is irreducible, certainly you cannot factor it further. It is prime as we have a PID, and irreducible and prime mean the same thing. So I is prime because it's an ideal generated by a prime element. Even though, for example, x squared minus 5x plus 6 is not prime, it factors, right, as x minus 3, x minus 2. And this guy also should, I think, probably has an x minus 2 hiding in it because the GCD is x minus 2. So both of our guys factor. Nevertheless, the ideal that they generate together is a prime ideal.